Hi there, welcome to Casual F# and welcome also to the second video in the series How to Write an F# Function. And in this video we're going to look at how to implement the project that we started in the previous video, where we set ourselves the task of reading some shape files and rendering an image of the building footprints that are in that shape file. If all of that means nothing to you, please go back and review part 1 because you'll be missing some context otherwise. And you might remember that we got as far as coding up the actual pipeline and sketching out or stubbing out the functions that we're going to have to call from that pipeline, but the body of each function is not implemented. But we started that process by making sure that the signatures of our functions are correct. So it's going to be pretty hard to kind of write the wrong body and still produce the correct function. So we've kind of set ourselves up for success. A couple of caveats. This is a bit repetitive, but we're not going to worry about performance at this stage. We'll do that in a separate video. And of course, this isn't any substitute for a proper GIS system. This is really concentrating on the craft of F# coding rather than on the correct implementation of a GIS system. So with that in mind, let's go ahead and implement our first function, which is load buildings. And that's got to take a directory path and a file pattern and produce a sequence of buildings. And you might remember that building is actually under the hood a sequence of polylines wrapped up in the single case discriminated union, and a polyline is just a sequence of points. So pretty easy start. We've opened the system.io namespace, so we should be able to say enumerate files for the directory path in question and for the file pattern in question. Take the sequence that will result, the I numeral that will result, and for each of them produce all the buildings that are in that file. But we don't want a sequence of sequences as a result of this, so we're going to use seek.collect. And what seek.collect will do is run a function and produce a sequence of sequences, but at the end of itself it will concatenate all those sequences together. Enumerate files is going to give us some file names, so we can use that in the lambda argument. We're going to make a shapefile instance using this easy GIS that we added through NuGet in the previous video, which we can instantiate by using a file name. And then, I think we established this in one of my other videos, you can do a seek.init, and that sequence is going to have record count as its number of items, which we can get, if I type it correctly, which we can get from the shapefile. And we're going to populate each item in the sequence by doing a get shape data, again on the shapefile. Now if that's a little confusing, let me just write it out in slightly longer form. Init will give you an I value for each item it instantiates, and shape data wants a record index. So that's kind of the long form of the same thing, but we can actually, every time you see this pattern here, where you've got a lambda function that's just feeding an argument back into its body as it were, you can get rid of the lambda-ness and just directly call the function like that. And actually that's the end of that step in this little mini pipeline. So at this point we're going to have a sequence of polylines. And if in this process you're kind of confused about what you're going to be getting, my tip is to just say funx and close the brackets like that. And then if you hover over the x, it's going to tell you what the type is, what the inferred type is of x, and that will kind of refocus you on where you are in your pipeline. Now that is a read-only collection of points. Let's actually make a better name for that now we know what it is and call it a point group. Actually it's point groups because it's a sequence of collections. And then we need to convert those into polylines. So I'm going to say point groups. It's a sequence so we can map it. Then each group is a series of points. Again, I could have done the X trick just to find out where we were at that point. Yeah, a point F array. So let's just call that points. Take those points, make them into a sequence. The reason being that we've said that polyline is going to be a sequence. And since at that point we've got a sequence of points, we can actually go straight into the kind of secret constructor, if it were, of the polyline single case discriminated union. And there we go. Don't worry about the red squiggly, because of course we haven't quite matched up with the signature we're expecting. Now again, let's just, if we've forgotten where we were, which I very often do the X trick. What have we got at this point? I missed out the fun keyword. Now we've got a sequence of polylines, and lo and behold, that's all we need to construct a building. So I could just say seek map building. Now, if you're being super astute, you'll realize that this here kind of matches the same setup that we had up here, where I said you can get rid of the lambda. And in fact, what I could have done is actually compose seek.ofArray and seek.polyline into a single function, and that will do the same thing. Actually, I'm not an enormous fan of doing that in every case. It's kind of useful for your audience, whoever's reading and maintaining your code, to have a breathing space where they can see where we are, and if we have a nice explicit value there, they can hover over it and see what the type is, and again kind of reorient it themselves. Well, that kind of looks like it's fairly credible. No red squigglies, so it must at least be doing something that matches the type signature. So we'll leave that at that. Okay, let's move on to finding the buildings. We need to find buildings between 2 points, given what I've misspelled there, a sequence of buildings, and return a filtered sequence of buildings. So I'm just going to start with the end of the function, buildings. This is clearly a filtering operation, and I could say fun building within P1, P2. And I think that will do the trick. So now we're going to need this building within function. It's going to take a building. And you might remember, I think we've mentioned this in one of the other videos, if you have a single case discriminated union, you can declare your function arguments in that style, in other words, the other way round and with no colon, and you'll actually have direct access to the payload of the single case discriminated union, in this case the sequence of polylines in the body of the function. So you don't need to explicitly pattern match within the body of the function. So what means that a building is within a bounding box? Incidentally, we don't need to provide P1 and P2 arguments because we're still within the scope of P1 and P2 here. And I'm going to say that a building is deemed to lie within a bounding box if any point of the building is in the bounding box, so even if it's just a corner. So if there exists some element in the building polyline that is within the bounding box. So again, we'd have a function called polyline within. So we need to define that. Same trick. Single case discriminated union. So that refers back to this here. And you might guess that we're going to do something very similar. Seek.exists point within. So the polyline is within the bounding box if any point on the polyline is within the bounding box. So its functions all the way down. This is going to take a conventionally declared pointf argument because we're talking about an individual point and whether that's within the bounding box. So we're going to say if p is between, we haven't defined between yet, but that's fine, p1.x, I should have said x here, and p2.x, and double ampersand p.y is between p1.y and p2.y. Well, we don't actually need an if statement because the Boolean logic of that will return true if the point is between the bounding box points. So finally we need to, I misspelled that by the way, define between, and we're going to have to be a bit careful about this because the point to the bounding box might be specified the wrong way round, so like the bottom right before the top left. So we can say between, apologies by the way for the constant helicopters going over, I live near a very large helicopter base, min and max for some value n, and we're going to deal with that issue of whether the bounding box is defined backwards by saying let our lower and upper bounds be if min less than max, then the lower is min and the higher is max, otherwise the lower is max and the higher is min. And then we can say we'll make it an inclusive between. There we go. So I think that should be a pretty good piece of logic. I guess the one disadvantage of these inner functions is you can't explicitly have unit tests just on those, so you have to make a kind of judgment call about whether you use inner functions or whether you have proper tests for them as individuals. It depends on their complexity. And I just realised I mistyped something slightly here. I should have said building there because we took the P1 and P2 parameters straight from there because they're within scope. And that seems to compile, no red squigglies, and again we'll get rid of our lambda function because we're just taking its argument and feeding it back in. So we can say there we go. Again, that at least seems to match the function signature we said. This is probably the hardest part, rendering. And again, thinking back to the last video, you might remember we said we'd only need the width because we can work out the height of the bitmap we need from the aspect ratio. That is the ratio of width to height of the bounding box. So let's calculate that. In case things are backwards, let's take the absolute value of that, and since these actually are float 32s, I'm going to actually make them into a pure double precision floating point value. So what's the bitmap height going to be? It's going to be that. We seem to have a sensible type for it, an integer. And we also want a scaling factor so that we can fit these points, which are values between 0 and several 100,000, I think, for the UK grid, back to the bitmap size. So we're going to say I'm slightly wondering whether that was the wisest piece of casting there. Let's just take that out and see how we go. That seems to be fine, so maybe we won't have to do that piece of casting there. Actually, I guess probably we do need that to be a float because we certainly don't want an integer as a scaling factor. Let's see how that pans out. So now I think we can make a bitmap because we've got all the dimensions we need. We've got a width for it and we've got a height for it. And we've got access to the bitmap type because we added a reference to system.drawing and we opened the namespace up there. Right, we've got a bitmap. Another thing we're going to need for correct positioning actually is the kind of offset of the left and bottom edges of what we want to plot, because you don't want to be plotting 300 miles north of the south coast or 300 miles east of the west coast on our bitmap. We want the bitmap to be nicely centered on the bit of building or the set of buildings that we're plotting. So I'm just going to get the whatever is the left hand most of the 2 points of the bounding box, and whatever is the minimum y. That will pay off in a moment. Right, we need to get the graphics drawing object from the bitmap. And we will need to get a nice smooth rendering by saying something smoothing mode, anti-alias. Now, to get things in the right place, we're going to make sure we offset by min-x that we calculated before, and we're going to scale by scaling factor that we calculated before. Likewise, and this multiplication, the scaling factor here, is to make sure that we're offsetting in the right units. Now we actually need to scale the drawing on the bitmap. So we will say scale transform, and we'll just use scaling factor twice. Make ourselves a brush with the foreground colour, which we pass in from here. Let's now clear the bitmap. I see we're getting a red squiggly up here for aspect ratio. Yes, I just typed aspect ration. Can't be right. Oh, I did need to cast this to float, and I did need to cast this to float 32. So I was a bit rash in taking those castings out. I missed out the keyword min there. Right, and this last red squiggly is simply because we haven't finished the function. Right, so now I think we can probably go ahead and plot the buildings. So take our buildings, and this is going to be an imperative operation. We're doing something rather than getting something, so that's a seek.iter. And the building is a sequence of buildings, so again we can use that single case discriminated union trick of pulling out the payload like that. And then for each building, it's an individual building at this point, again iter. The payload of the building is a polyline that describes at least part of the building. And this is the nice thing, graphics has a fill polygon there, which takes a brush argument that we've made above, and we've got our polyline. It's a sequence at the moment, so we'll just need to make it into an array. Close the brackets, and there we go. Now I suspect if we just return the bitmap now, because remember, if we just scroll out a bit, zoom out a bit, yes, this needs to return a bitmap, so we need to return that bitmap that we have mutated here. And our squigglies have gone away, so that's looking good. Now I happen to know that the UK coordinate system is a different way round from the painting system, certainly on Windows and on most computers, which would mean our buildings came out upside down. So the final thing I'm going to do, and I probably could do this with transforms, but this seemed more straightforward, do a rotate flip. None flip Y is what we want, and that will just do a vertical flip, so we've got the buildings the right way up. Right, so that's our complicated bit. We need a save bitmap function. Should be fairly straightforward. Just do a save on the bitmap. So really that's just a wrapper to make bitmap.save nice and composable. And look, all the red lines have gone away, so presumably we're done. Well, there's only one way to find out. I'm going to add a runner program. We could do this in script as well. So I'm going to add a new project. I'm going to make this a console application, and I'm going to call it OS Buildings Demo Runner. I'm going to add a reference to the project we just wrote. I'm going to do some opens. Not sure we need that system.drawing actually. We certainly need a reference to it because this is going to be actually doing the drawing, I suspect. So system.drawing, and we also need to open buildings.drawer. There we go. Now I'm actually going to cut and paste the call to this just so you don't sit there watching me type paths, but I will take you through what I typed. Just need to make sure we return something from our main function. So what did I type? A path to my shapefile set. Let's actually use all the shapefiles for now. And I have got the coordinates there for a bounding box around Heathrow Airport. Let me just show you how I got those coordinates. I went to streetmap.co.uk. I searched for Heathrow Airport. I did a move arrow and I clicked somewhere. Then I just copied the X and Y coordinates from the URL and I just repeated that for a point down here somewhere. Then let's make ourselves a nice fetching colour scheme. Let's go for crimson on antique white. That sounds quite nice and crisp. I've gone for a massive bitmap. There is an upper limit actually, but 10,000 seems to be okay. Right, that looks like it's going to run, so let me just save and run that. Now if you run this, you'll find it takes a few minutes to run because we haven't done any optimization. We are dealing with a fairly sizable data set. Okay, there we are, that's finished. So let me just bring an Explorer into view. We do seem to have a pretty picture. And there we are, there's Heathrow Airport, unmistakable profile. And if we zoom in, we'll see that actually the OS data has really got an exquisite level of detail, and it has rendered really nicely with the anti-aliasing switched on. And we've even got all these crazy English style meandering estates around the airport as well, again rendered in really considerable detail. I think one of these is Terminal 4 and maybe that's Terminal 5 just off the picture there. Okay, so there we go. That works. It needs a whole load of optimization, which we'll do in another video. And remember, this is no substitute for true GIS. This is really a demonstration of F# design techniques and syntax rather than some instruction manual on implementing a GIS. Couple of acknowledgements, well, 3 to be precise. Thanks to Alistair Ray for inspiring all this. Thanks to the Ordnance Survey Open Buildings project. So this is Ordnance Survey data from 2017. And thanks to Huasian.easygis shapefile lib, which does the heavy lifting of reading the shapefile libraries. Now I'll put a link to the source code in the comments of the video. Let me know if there's something that's unclear or there's something you'd like me to add to some future video. In the meantime, thank you for listening to Casual F#. Tune in again soon. Bye.